Example 5 has h of x is equal to x over x squared plus 1. Again, since we're not told anything, we're looking at the interval from negative infinity to positive infinity. Now, we didn't talk about this last time, but recall this says that f has to be continuous on the open interval. Well, quadratics are continuous everywhere, so it was continuous on its open interval. So now we have to figure out, well, is this rational function actually continuous on that interval? To determine this, I have to set the denominator equal to 0 and solve for x. And if I end up with any real numbers, then I'm not continuous over the interval from negative infinity to positive infinity. So solving for x, I get x squared is equal to negative 1. Taking the square root of both sides, I get x is equal to plus or minus I. Well, I is not a real number, so that means yes, I am continuous over that interval. So now what I need to do is find the first and the second derivative. Well, this is a quotient. Since it's a quotient, I'm going to need to use the quotient rule. So I get h prime of x is equal to the bottom times the derivative of the top. Well, the derivative of x is equal to 1 minus the top times the derivative of the bottom, which is 2x, all over the bottom squared. Now, since I need to find the second derivative, I am going to need to clean this up. So h prime of x is going to equal, well, anything times 1 is itself. And then x times 2x is 2x squared. Here, my x squareds are like terms, and I end up with h prime of x is equal to negative x squared plus 1 all over x squared plus 1 squared. Then I need to find the second derivative. Well, the second derivative, again, is another quotient. So we're going to say h double prime of x is equal to the denominator, x squared plus 1 squared, times the derivative of the numerator, which is a negative 2x, minus the top, negative x squared plus 1, times the derivative of the denominator, which is 2 times x squared plus 1 raised to the first power times the derivative of the inside, which is 2x, all over the denominator squared. And what we want to do is do our best to clean this up as well. So h double prime of x is going to equal, well, let's try to factor out the greatest common factor from these things. If we take a look at this term here, and this term here, I might be able to tell that I have, for both of them, a negative 2x that I can pull out. And for both of them, I have an x squared plus 1 to the first power. If I were to pull those things out, well, from this first term, all I'd be left with is one of the x squared plus 1s. Since I pulled out that negative, here, this becomes a plus sign. I still have this negative x squared plus 1. And I still have this 2 because I pulled out the 2x and I pulled out the x squared plus 1. And this is still all over. Well, now power to power we multiply, so this is x squared plus 1 to the fourth power. Well, let's distribute and combine like terms here in my brackets. Now, when you're combining like terms in those brackets, I'm just going to do it a little bit above so we can save some space. We'd have x squared plus 1. Here, if I distribute my 2, minus 2x squared plus 2. Also, you might notice that x squared plus 1 and one of those will cancel. So I have that h double prime of x is equal to negative 2x. Combining like terms, well, x squared minus 2x squared is a negative x squared, and this becomes plus 3. And that's all over x squared plus 1 to the third. And we can stop now. All right, so now I need to find my critical numbers. So let's go ahead and find my critical numbers. So over here, if I find the critical numbers, recall, that's going to be places where this thing is equal to 0. So if I set negative x squared plus 1 over x squared plus 1 quantity squared equal to 0, well, I can always put it over 1 and cross multiply. Well, 1 times negative x squared plus 1 is negative x squared plus 1. And 0 times x squared plus 1 squared is 0. So solving for x, first I subtract 1 from both sides. Then I'm going to divide both sides by a negative 1 to clear that negative out. And I get x squared is equal to 1. Then I take the square root of both sides to solve this, and I end up with x is equal to plus or minus 1. Now that's more than one critical number, right? That's x is equal to positive 1 and x is equal to negative 1. So technically, I don't exactly know if one of these is going to be an absolute max or an absolute min. I'm not really sure. So I am going to need the graph to look at this. But what I'm going to do before I grab the graph is actually evaluate. I'm going to figure out what is the second derivative evaluated at 1. And what is the second derivative evaluated at negative 1? So we're going to do that first, and then we're going to look at this on a graph. So plugging in a 1, again into the second derivative, it's going to be parentheses, negative 2 times 1 times negative 1 squared plus 3. And I needed parentheses around that whole entire numerator, so I'm going to go ahead and just insert that. So negative 2 times 1 times negative 1 squared plus 3. And then all of that gets divided by, and then this is 1 squared plus 1, and that's to the third power. And I end up with negative 1/2. Well, since that's a negative 1/2, we know that we would end up being concave down. And if we're concave down, that guy should be a max. What happens at negative 1? Again, grab a calculator and let's look this out. So again, it's going to be parentheses to start it, and then parentheses negative 2 times negative 1. Then a parentheses for the negative of negative 1 squared plus 3. Then close the parentheses for my numerator, and I'm dividing that by negative 1 squared plus 1 to the third. And I get positive 1/2. So if that's positive, I know that I would be concave up, which means that I have a min. So one of these looks like it might be a min and the other one might be a max. Well, let's grab a graph and let's figure this out. So we have y equals, again, the original is x divided by x squared plus 1. Well, notice this actually does have an absolute minimum and an absolute maximum, because the graph goes to a lowest point and then it goes back towards the center and to a highest point and back towards the center. So this graph actually does have an absolute max and an absolute min. So we did have to check it with the graph, but these are going to be our absolute maxes and mins. So then for this particular graph, we say that we have an absolute max at h of 1 equals, well, if we plug 1 into here, we can use a calculator. I'm just going to skip that part. So if I plug 1 in here, I end up with 1 over 2, which is 1/2. And I have an absolute min at h of negative 1 equals, well, if I plug negative 1 into here, I end up with negative 1 over 2, so negative 1/2. So for this one, I did have two critical numbers, so I had to actually use the graph just to ensure that there was going to be a max or a min. Okay, our last one, find the absolute maximum or minimum value on the interval from 0 to infinity for this function. Is it continuous? Well, remember, this is a rational function. So if I set my denominator equal to 0, I get x equals 0. So that means that I'm continuous from negative infinity to 0 and from 0 to infinity, which means I'm continuous on that interval. So I am continuous. So now it's time to find the first and second derivative. So if I find the first derivative, f prime of x is going to equal, well, the derivative of 4 is 0. The derivative of x is 1. And then 9 over x, recall that that's the same as 9x to the negative first. So if I'm finding the derivative there, that would be minus 9x to the negative second. So let's find the second derivative. So my second derivative, f double prime of x, would equal, well, the derivative of 1 is 0. I don't need to write that. Negative 9 times a negative 2 is a positive 18, x raised to 1 less to the negative third. So now let's figure out where in the world is this thing equal to 0. So I have 1 over, well, if I rewrite this as 9 over x squared equals 0. So the first thing I want to do is I want to move this 1 to the other side. So I get negative 9x squared is equal to negative 1. Well, since I have a negative in both sides, those kind of cancel out. So I just have 9 over x squared is equal to 1. Well, I can always put this 1 over 1 to cross multiply to solve for x. So if I multiply here, 9 times 1 is 9. And 1 times x squared is x squared. If I take the square root of both sides to solve this, I end up with plus or minus 3 is equal to x. Well, that's two critical numbers again, right? We have x is equal to 3, and we have x is equal to negative 3. But recall, our interval is only from 0 to infinity, so we can't use this critical number because it's not in our interval. So what we need to do now is again evaluate it at the second derivative. So I need to figure out what is f double prime of 3, which is going to be 18 over 3 cubed. And again, if we grab our calculator, 18 divided by 3 to the third is a positive number. And if it's positive, we know that we are concave up. And if we're concave up, that means that we're going to have a minimum value. Therefore, we have, in this case, an absolute minimum at f of 3. Again, we're going to need to plug it back into the original function to find the y value. So, plugging it back into our original function, we get 4 plus 3 plus 9 over 3, which is 10. So, f of 3 is equal to 10. And since I only have one critical number, I know this is my absolute min, and therefore I'm not going to have an absolute max. That's it for section 4.5.